for our disc and washer method, we stacked areas, right? So we stacked circle areas, right? I had one coin, right, on top of another coin, on top of another coin, on top of another coin to get, right, stacked coins or discs, right, to create a volume. Whether the coins had a hole in them or not, right? Yes, you with me there? Right, when the coins have a hole in them, we're talking about washer. When they're solid, we're talking about discs. So, but either way, we're stacking areas. And once I get a bunch of areas stacked, I multiply those areas by that height, and I get the volume. So, but what we're going to do in the shell method, and these are cylindrical shells, so cylinders, cans of soda or empty cans of tuna fish, right, kind of thing, is we're going to be stacking circumferences. We're going to stack the circumference. So I'm kind of think of it's the Russian dolls kind of thing. Right? Do you know those Russian dolls where you take off the top of one doll and inside is an exact replica but smaller, and then take off the top of that one and there's another one inside, etc., right? So that's what we're doing. We're stacking empty cylinders inside of each other, right? So what do we had here? We had a pi r squared times a width of the coin, right? And what do we get for a circumference? We get a 2 pi r, right, times a delta x, I'm sorry, a 2 pi r times the height of the can times the width of the can. Right, so this is my height, and then you can kind of imagine the thickness of the metal, right? There's my dx, the thickness of the can, right? I think I have a nice visual here. Let me see if I have. I used to have it. Maybe it's in my bag. Hold on. No, I can't find it. So I think the Russian dolls is a good picture of it. I used to have a drinking glass for camping where you could compact it, right? It would go down to a single thing, and you could see all the rings inside of each other, almost like a telescope, too, right? If you could imagine pulling out the telescope, right? All of those kind of the rings inside of the rings, kind of thing. So, if you can see my three variables here, you can definitely see the three variables here. My dog just freaked out because I'm looking for this thing. R times delta x. There's my three variables for volume. R times height times delta x. There's my three variables for volume, right? So the only thing that's kind of tricky on this is, well, first of all, shells are parallels. I know it's probably not proper English, but it's how I remember. Shells are parallels. Everything else is perpendicular. right? And then r is the distance right to left, or upper minus lower, from the axis of revolution to that initial rectangle. The height is the height of the rectangle, upper minus lower, or right minus left. But not taking in the axis of revolution, right? In that particular case, I'm not going from the axis. I'm going from the axis to get the radius of my circumference, 2 pi r.
Sorry, what did you write? R is the distance from axis
of revolution to the rectangle.
Oh, okay.
Yep. And I'm not putting in there that upper minus lower or right minus left, because that's our theme throughout. We're always going to be trying to get positive distances. And the only way to do that is higher y value minus lower y value, or further right x value minus further left x value. Well, what's nice about this, and I have done this on the test, is I can give you the same problem, right? I can give you the same problem that should give me the same volume, once using a disc or washer and once using shell. So let's do that one first, right? So something nice and symmetrical, square root of x and x squared, right? So I'll make my square root of x into green, right? And my x squared in green and square root of x in blue, just so we can see the two. So we want to do this about the y-axis. And that will be shells. And about the x-axis, and that will be washer or disc. You know what I mean? I almost think of them the same and just decide later if the coin has a hole in it or not. So let's do our shell first. So shells are parallels. So to the y-axis, I am drawing my rectangle like this. And if I ghost that one, right? If I ghost that particular one, I could see my empty tuna can here. And that's one of my stacked cylindrical shells. How you doing? You with me? So the shells method is kind of nice because you don't care if there's a hole in it or not, right? Doesn't matter. So my axis of revolution to that original rectangle, right, is this distance right here, this red distance. And from the axis to some distance to the right, what letter would you use for that? What variable would you use for that?
X.
X, exactly. So the radius usually will be pretty easy to figure out. But we always have to do right minus left when it's a tricky, always, but when it's a real tricky axis of revolution, then you have to think a little bit. the function is pretty clearly square root of x minus x squared, right? The height is so r we got as x. We got our height as what? The blue minus the green, right? And then look at the width of my rectangle. It's definitely a delta x problem. So I'm doing.
Can you explain how you got r equals x again?
Yes. So can you see my red arrow on the picture?
Mm-hmm.
So I'm starting at the axis of revolution and then moving over to that first rectangle that I drew. In fact, let me erase other stuff here. Right? So I'm drawing from the axis of revolution to that rectangle. And I'm trying to figure out what distance that is. Well, the rectangle is arbitrarily placed, right? The rectangle should be anywhere in that area, right? And so what distance would I call that? X. So if I have a distance up, it'll be called y, right? Will it always be x or y? No. You have to take in the distance from the axis of revolution to the rectangle. And we'll do one like that so you see it. So this is the integral from 0 to 1 of 2 pi times our r, which is x, times our height, which is square root of x minus x squared, times dx. So now we're just racing, right? You and I are racing, so we're doing so on your mark, get set, go. How we do? Anyone get there? A bit of chat, sorry. Haven't been paying attention today. Nice, Melky. Good.
Yeah, I have a,
Yes, Charlie.
why the heck is x minus x squared instead of x squared minus square root of x?
Yeah, so if I'm looking at that original rectangle, what's the upper part of that rectangle? What function is touching the upper part?
Oh, the upper part is square root of
Yes,
x?
yes.
Oh, I got that.
Yep.
Okay, thanks.
If I'd switched them, I'd get a negative. That's all.
Yeah, I mean, I thought like the upper part is x squared.
Yeah, but you see what I'm saying? Yes. Oh yeah, you saw them switched. Yeah, yeah. I like to put a color on there just so I can, because I will sometimes switch them too. You know. And if you, like I had a student in Calc 1 last semester who had some dyslexia. Yeah, it's very tough. I'm sure it's very tough, even in mathematics, when you're switching things around. So, you gotta, I'm sure you've come up with tricks by now. If you've made it all the way to Calc 2 and you have some kind of, disability in terms of learning, I'm sure you've come up with tricks. So I like the MindTap problems the same, 1 to 17 in 6.2 and 6.3, right? All right, let's do the same problem. We should get the same result if I rotate this around the x-axis. Right? Do you agree with that, first of all? Do you see that if I rotate this thing around the y-axis, I get this kind of flower, I get this kind of teacup with the funnel inside. And then if I do it here, I get the same exact picture, right? I get the teacup on the outside with the kind of funnel inside, right? Mr. Toad's Wild Ride or some stupid kiddie ride like that. So let's see if we get the same volume, right? Will I always get the same volume if I rotate around the x-axis or y-axis? No. But in this case, I have the symmetry, so I do have the same volume. Okay, so let me go to a brand new page just to start this one. So my goal, I've got square root of x and x squared, right? And now I'm going to do x-axis. So perpendicular to my axis of revolution. Oh, isn't that nice? Perpendicular to the axis of revolution still gives me a function of x, right? But I need a large R and a lowercase r, right? So who's got large R for me? Class. And lowercase r is x squared. So my volume is pi times the integral from 0 to 1 of minus lowercase r squared dx. Everybody with me there? Everybody okay on that setup? So we're doing a washer method here, right? Everyone see it's a washer.
No.
So if I ghost it, right, and this is what I want to do, and then rotate it, so you can see I got a nice teacup on the outside, right? So there's my outside, and then I'm going to show you the ghost of the inside, which is all empty, right? The inside is all empty, so that filter, right? So now I'm kind of superimposing the two on each other, right? Superimposing the two on each other. And then I want to cut through it. So I'm going to cut right through here, and I'm going to see the empty blue, right? The empty blue is the center of my cup, and the black is the thickness of my cup. So right here is that rectangle, right? Rotated over. So there's the rectangle rotated over. And then in here is that empty piece.
Okay, I see it.
Nice.
Thank you.
Yeah, it's tough. It's tough. The geogebra.org will help a little bit if you look around in there and find a couple that will give you a visual of this. So I think we're racing now, right? And we can result. let's jump to one from the exam, and then we can quit for today. I will be around till 11:30 for office hours. I'm actually around till I'm hovering around my computer until 2:30 every day this week. Okay, so you can come back. I'll hear a sound, right? Let's pretend I'm emptying the dishwasher or some stupid list. Or let's say I'm taking the garbage out. Okay, I take the garbage out. So you come into the room, it makes a sound, and you go, Professor, Professor, and then wait for me. If I'm taking the garbage out, I'll be right back, and then I come into the room and check. Okay. I try to leave a note if I'm going to step out for a minute, but I'm a little forgetful. So, but I'm around. Okay. So just give me a minute if I stepped away. How much work did we do this weekend? How many hours?
I got a good amount in.
Nice. With success, Michael. Yes, you got things right.
Yeah, but like I said, the WebAssembly was pretty easy. I'm just scared about the midterm. They're gonna make everything hard.
Yes. Ask your brother. Ash, what were you gonna say?
I said I got through some homework, but med disability.
Yeah, I know it's tough. It's tough. You have to work when you're ready to work. But then hopefully we're doing things like exercising, or, you know what I mean? We got to be eating right.
Yeah.
We have to be sleeping right. We have to be doing things that will put us in the right energy and right space. And it's not easy. And I'm not just talking to you, Ash. I'm talking about myself as well.
Yeah, it helped when I had Coach early last semester. I'll say that for sure.
Yeah. It was nice to have. We had an embedded coach in our Calc 1 class, is what she's talking about. But you do have the Learning Center.
They don't always. It's usually a miss when they try to help me.
All right. Well, then it's me.
Yes, I know.
Okay. I mean, I'd rather everyone come to me first, but, if you have something that works, it's hard to change, I get that. Ashley, you were in class with Charlie last semester, so you certainly can, you two definitely, and there's a bunch of others in here that have me for Calc 1 too. Sarana, Leah, tonight, Angel. I think I got everybody. Jerusalem, right? So you all have had me before, so you're used to me, good or bad, but so you can possibly work with each other, right? All right, let's go to a final exam here. Give me 1 second to bring it up. I didn't post this one yet. But typically, this topic comes up again on final exams. Pretty sure it was final exam fall 2019. And I'll post all of these up in the next couple of days, because it's not a bad idea for you to look at the chapter 5 and 6 material on the final exams. Don't let this stuff scare you, okay? Here we go. This is a very long exam. A very, very long exam. I don't give long exams in this remote structure, so don't let it freak you out. Most of my exams in the past few semesters have been 5 questions. So we're looking at 17, 18, and 19. We're going to do, this will be our last problem today. Okay. So this is a chapter 6 problem that turns into a chapter 5 problem that shows up on the final exam. And so what am I saying to you here? This is one of the things that will show up again. So if you don't get it on the midterm, it'll show up on the final. And then you can finally show me that you get it, right? It takes some students a little bit longer. It's a quick turnaround here. You'll have a week now. You have more than a week to practice this stuff, right? But if you still owe me some work from chapter 5, you could be in trouble. But just get on it, practice, ask for help, okay? So we're gonna, number 17 says find the area of the region bounded by y equals ln of x, y equals 0, and x equals e. So we'll draw that picture or find that area. So that's really a 6.1 problem, or even, yeah, not even, right? 18, find the volume of that region using the shell method when rotating about the y-axis. So now I'm going to take that area and rotate it about the y-axis. And then that solid that I create is going to have an empty interior. I want to find the volume of that empty interior using a disk method, and then add the two volumes together and see what I get. Okay? So that's the idea. I don't expect you to know exactly what the hell I'm talking about yet, but we're going to do it now. I don't know if I have any final exams posted, but I will post a couple more midterms and a few finals right before, so you can work on things this week. And again, if you're looking at the final exams, you're looking for chapter 6 material, chapter 5 material. So so number 17. So this was fall 2019 final exam. Number 17. So we're taking the ln of x from 1 to e, and we're finding that area. So we're finding this blue area in here. So the area is equal to the integral from 1 to e of ln of x dx, right? And we've done this one already a couple times this semester, right? I don't think I have to do this by parts again for you, do I? So this is, right, this is x ln of x minus 1, sorry, minus x evaluated at e and 1. Does anybody want to see that by parts again?
Yes, please.
Yeah, so u is ln of x, right? E is 1 over x dx. Ash, you with me there?
Yes.
Yep. dv is the integral of dx, so that means v is x, right? And so I have uv. So let me not skip a step. uv minus the integral of v du. v du is x times 1 over x dx. And that's x ln of x minus the integral of 1, which is just x. The by parts shows up every midterm. The trigs, everything. I make everything show up. I work extra long hours just to get you to have every method on your midterm. So what do I get for this area? I get e ln of e minus 1 ln of 1 minus 1, right? And so this is e minus 0 plus 1. I just get 1. So the area is 1. How we doing? Uh-oh, did I lose someone else? 3, 6, 10, 14, 17. Who went away? I'm going to take attendance again, please. If you want to turn your camera off, feel free. I'll let you know when I'm done. Okay, got it. Thank you. So, we're ready for the next problem, right? Everybody agree with this? Everyone comfortable with this? It's easy, right? Nice. Serrana gave me the thumbs up, or she's hitchhiking. Nema, thank you. Ash, great. Adam, nice. Nice. Eruz, Charlie, thank you. Beautiful. So now, oh, chat, I got a chat. Where's my chat? Thank you, Melky. Nice. I close my chat every now and then, but sometimes I don't see it. So if there's something you chat at me and you want me to, and I don't, I'm an old man. What do you want? All right, same problem, but we're going to rotate now. We're going to get this volume about the y-axis. So shell method. Same problem, but volume around the y-axis. So here's my picture. I've got my function y equals ln of x from 1 to e, right? But I want to rotate around the y-axis, right? So I can see the ghost, kind of, right? And I'm going to see that this inside piece is empty, right? The inside piece is empty, like the top of a cooling tower of a nuclear plant, right? And the outside is a solid disk, right? The outside is a solid soda can, tuna fish can, whatever. I don't eat tuna fish. So and I'm shell method, right? I'm shell method. How do I know I'm shell method? Because I want to be, well, I told you, but if I am doing this axis of y and I draw myself parallel, why would I prefer to do that? Because I like doing things in terms of function of x. So I'm going to try and pick shell method in this case so that I get a function of x. Does that make sense? So my rectangle is parallel to the axis of revolution so I can see my delta x, right? I need the radius. I need the radius, right, to the rectangle from the axis of revolution. And that one again is x, right? So you should see that radius is x there. So my volume is going to come from circumferences. So 2 pi x function of x, which is my ln of x dx, right? And I'm going, so since I'm in terms of x, I'm going from 1 to e again. Make sure you're with me on the setup. Don't let me go too fast. Easy setup, more challenging integral. This is integration by parts again, right? But the setup is not difficult, especially if you have your formula sheet, which, by the way, I don't give you, right? You understand what I'm saying? You don't get a formula sheet, right?
Isn't it -x?
For the radius?
No, it's x ln of -x, isn't it?
Okay, so I'm just, remember, this is the height of my function. This piece right here is the height. And this is the, of my rectangle, and this is the width. And so I'm just looking at that rectangle. What is it hitting at the top? It's hitting ln. And then what's it hitting at the bottom? 0. So it's just ln of x is the height. Nema, yes? Okay, good. So this by parts is a little bit longer, but u again is ln of x. Du is 1 over x dx. dv is the integral of x dx. So v is x squared over 2. And then the interior integral there is pretty easy. Oops, sorry. I mean, you're not following me anymore. You're just doing it yourself.
Are we going to be doing anything besides volume? Are we going to be doing surface area or anything like that?
Yes, arc length and surface area is 6,4. Six five six six 6.5 is physics application, 6.6 is physics application, 6.7 is bio application, 6.8 is probability applications, and those are all independent study for your project. And you don't have to wait on that. You're ready to do those. When you do the project, read this section, do the examples in this section, and then if you get stuck on a problem, it's just like one of the examples in this section. Okay. How'd we do here? Anyone else get the same volume? Michael, what are you thinking about this? As you can see why this is a little bit more difficult than WebAssign, but this is a typical test question for me. Oh, maybe it's Michael that's gone. It is Michael that's gone. So, Michael, you must agree with me that you should give a few of your points to every student in the class for the final. All right. I want to now take, so if we look at this picture now, right? If we look at this picture, I've got a solid tuna can outside, right? So for example, this piece is completely solid all the way around, right? And then inside, in here, in the yellow piece, this yellow volume is empty. So I want to find that yellow empty volume using a disk method. So here we go, next page. Yes, you with me? Is it okay? Can I move on? Do you need more time?
Can you show the answer that you got?
One more time, Eleanor, say it again, broke up.
Can you show the answer you got?
Yes, pi over 2, all times e squared plus 1. Did you get there, Eleanor?
Yeah, I did. Thank you.
Nice. Lucy. Lucy. Stop it. It's mommy. Hold on, please. All right, it's mommy. Okay. What happened? Really? Really, sir?
Oh, I did $45.
Wow.
I'm
Quick.
a little early. Yeah.
I'm still in class. It's okay. Sorry, class. I just thought of a joke for swimming. Yeah, you went swimming, and I said, how many laps did you do? You could have said, I forgot, because you had a lapse. This is what it's like living with two corny mathematicians. It's horrible. She's over there going, oh. One of the best jokes my girlfriend ever wrote, she said, I'm so good at putting my contact lenses in, I can do it blindfolded. She's also Polish. She doesn't know when she's funny, but... All right, we're trying to get this interior volume now, right? So we've got our ln of x from 1 to e, but we're really interested in this particular empty volume here, right? Can you see that? So when I rotated that ln of x around, I had that empty interior. But now, so I'm still going about this axis, but I want to get this particular piece via the disk method. So I'm going to get that interior volume. This is number 19. And so disks are perpendicular, right? I'm remembering shells are parallels. Everything else is perpendicular. So I've got to draw my rectangle perpendicular to the axis of revolution. And the outer radius is pretty easy, right? So I know that y equals ln of x. But when I'm doing an integral in terms of y, I have to solve for x. So I get what x equals e to the y. So that outer radius is e to the y now. How you doing? Are you with me there? My dog's building a nest. She's hiding a biscuit. Okay. So the volume is going to come from pi r squared from 0 to 1. Right, because I'm going in terms of my y direction, I have to go from 0, that's my base, up to where ln of e is, which is 1. And I need my function squared, so e to the y squared dy. E to the y all squared, right? How are we doing there? Lucy, make your bed already, come on. It's the middle of class. You're making too much noise. So I have pi times the integral from 0 to 1 of e to the 2y dy. And I make a u sub of 2y, and so du is 2 dy. So I need the 2 and I need to cancel it. Yeah, what are we doing here? And there's our interior volume. Whew, what a tough. Well, this is 3 questions, right? We're still on the kind of the third one here, right? But I certainly could see this being 1 question on your test. Now, I want to take those two. Anybody get there? Anybody get there? Anyone need more time? Tell me what you need. Tell me what you want. What you really, really want. Ashley, you there?
Yeah.
Nice. So what I want to do is I want to put these volumes together and show me that it gets me the volume of a cylinder, right? I'm going to put these 2 volumes together. I'm going to put that outside volume and that empty interior volume together, right? So I think my outside volume was pi over 2 times e squared plus 1. And my inside volume was pi over 2 times e squared minus 1. And pretty clear, if I put these 2 volumes together, I'm getting pi over 2 times pi over 2 times e squared, which is just, I'm sorry. Yeah. I get pi over 2 e squared plus pi over 2 e squared, which is 2 pi over 2 e squared. So that's pi e squared. So there's my volume if I put them together, if I add those 2 volumes together. And why am I saying that's significant? Because it should just give me the volume of that cylinder in total, right? It should just give me that volume of the cylinder in total. So how do I get the volume of a cylinder? It's just pi r squared height. And the height is 1, and the radius is e. So I get pi e squared times 1, which is, there it is. See? So, I mean, the setup is easy. The integrals, I mean, it's not much more difficult. But again, I'm saying, why did we do all those integrals in Chapter 5 and then have them just go away? So, so you got some MindTap to do. You have some WebAssign to do. I don't give shawms on these. The shawms are a little bit too complicated. They're actually not horrible. If you really wanted one, you can have it. But I like Paul's notes. If you want to do something else, you can do Paul's notes here.